This idea challenges the very foundation of causality, the principle that causes precede effects. In the quantum realm, the timeline of events becomes fluid, and the observer seems to play a role in constructing the narrative of reality itself. Wheeler's conclusion was as poetic as it was scientific, that the universe may be a kind of self-excited circuit, in which observation by conscious beings helps the cosmos to know itself. Still, many physicists resist drawing philosophical conclusions from such experiments. They argue that observation need not involve consciousness, that any interaction capable of extracting information from a system qualifies as a measurement. When an atom emits a photon and another atom absorbs it, that interaction constitutes an observation. It is not that the atom is watching, but that information has been exchanged and the system state has been defined. This viewpoint suggests that observation is a fundamental physical process woven into the dynamics of energy and matter, not something dependent on human awareness. Yet even this mechanistic view does not fully remove the strangeness of observation. Whether through a conscious observer or an unconscious interaction, the result is the same. Reality crystallizes from a haze of probabilities into a single outcome. It is as if the universe, in every moment, must decide what story to tell, and observation is the mechanism through which that decision occurs. The implications of this reach far beyond the laboratory. They touch on the very way humans understand perception, knowledge, and truth. For centuries, science has been built upon the assumption of objectivity, the idea that facts exist independently of those who discover them. But quantum mechanics suggests that objectivity may be an ideal rather than an absolute. Every observation carries within it the fingerprint of interaction, the subtle exchange that binds the observer to the observed. This does not mean that reality is subjective, but that it is participatory, a collaboration between systems, each influencing and defining the other. Consider how this idea ripples outward into other realms of science. In cosmology, for instance, the role of observation becomes significant when considering the early universe. The Big Bang, the event that gave birth to space and time, produced a universe filled with quantum fluctuations, minute variations in density that later grew into galaxies, stars, and planets. Some cosmologists suggest that these primordial fluctuations only became definite through interaction and observation. In that sense, the seeds of cosmic structure may themselves have been shaped by the same principle that governs subatomic particles. The entire visible universe could be the result of quantum observation on a grand scale. As technology advanced, new experiments allowed scientists to probe observation at ever finer levels. Quantum computers, for example, rely on superposition and entanglement, states that collapse the moment they are observed. Engineers must design systems that maintain quantum coherence by avoiding measurement, allowing qubits to exist in many states simultaneously. In a very real way, the success of quantum computation depends on controlling observation itself, on knowing when to look and when to let the system evolve unobserved. Observation, once a simple act of inquiry, has become a tool to be engineered and manipulated. In this new era, the boundary between physics and information theory has begun to blur. Some researchers propose that reality is fundamentally made of information, that the universe is, at its core, an immense informational network. Observation, then, is the act of reading and updating that information. This idea finds resonance in Wheeler's phrase "it from bit," meaning that every physical thing, it, ultimately arises from a fundamental binary choice, bit. According to this view, The act of observation is the process of transforming potential information into actual experience. Reality, therefore, is not merely material but informational, a living web that evolves through the exchange of data. Still, the philosophical tension remains. Does observation require awareness? Is consciousness itself a quantum process that participates in the collapse of the wave function? Some interpretations, like the consciousness causes collapse theory, suggest that only a conscious mind can turn probability into reality. Others reject this, arguing that consciousness arises from classical processes far removed from the quantum scale. Yet, the very fact that such questions arise shows how deeply the nature of observation unsettles traditional boundaries between science and philosophy, physics and metaphysics, the external and the internal worlds. When viewed from a historical perspective, the transformation of observation in physics mirrors the transformation of human thought itself. In the classical age, humans stood apart from nature, observing from a distance and decoding its rules. In the quantum age, humanity has discovered that it cannot stand apart, that the act of observing is an act of participation, that the observer and the observed are part of a continuous whole. The universe is not a painting to be admired from afar. It is a symphony in which every note, every listener, and every moment of hearing contributes to the music itself. This realization has inspired profound reflections in the philosophy of science. It suggests that the search for knowledge is not a journey toward an external truth, but a process of interaction with reality, a mutual unveiling. Observation is not about uncovering something fixed and immutable, but about participating in the ongoing creation of meaning. In this sense, science becomes a dialogue between humanity and the cosmos, a conversation written in the language of experiment, mathematics, and wonder. And yet, the mystery endures. Despite decades of research, physicists still debate what exactly happens during observation. Is the wave function's collapse a real physical event, or merely a change in our knowledge? Does reality exist in definite form before it is measured, or does measurement bring it into being? No experiment has yet given a final answer. Instead, every discovery seems to open new layers of depth, reminding us that observation is not a solved problem but a living question, one that touches the core of existence. The power of observation lies in its dual nature. It is both a method and a mystery. It allows us to see, to know, to measure, and yet it reveals that seeing, knowing, and measuring are not neutral acts. They are acts of creation. The scientist with a microscope, the astronomer with a telescope, the engineer manipulating qubits in a lab, each is not merely uncovering a pre-existing truth, but helping to shape the form it takes. In this way, the nature of observation transcends physics itself. It becomes a metaphor for human experience. Every act of perception, every moment of awareness, is an observation, a collapse of infinite potential into a single lived reality. Just as the quantum world resolves into definite states when observed, so too does human life take form through attention and perception. We bring the world into focus through the lens of our observation, and the world, in turn, defines us through the responses it gives. Perhaps this is the ultimate lesson of the observational problem, that reality and observation are not opposites but partners. The universe is not something that stands apart from us, waiting to be measured. It is something that unfolds through our participation, through every act of looking, wondering, and questioning. In the smallest flicker of an electron and the vast swirl of galaxies, the same principle may be at work. The dance between potential and actuality, possibility and perception, existence and Observation. In the end, the story of observation in physics is not merely a story of scientific discovery. It is a story of awakening, of humanity realizing that the boundary between the observer and the observed, between self and universe, may be an illusion. The cosmos is not a distant spectacle, but a living mystery that reveals itself in the act of being seen. To observe, then, is not only to measure, it is to participate in the very act of creation. And so, as physicists continue to probe the unseen depths of matter and energy, and philosophers continue to ponder the meaning of existence, one truth remains. Observation is both the window and the mirror of reality. Through it, we glimpse the workings of the universe, and through it, the universe glimpses itself. In the vast story of science, one of the most fascinating realizations is that the observer is not merely a witness to the universe, but an active participant in shaping it. The idea that the act of observing can define physical reality challenges the very foundation of classical thinking. In Newton's world, objects existed in a fixed state, independent of who was watching. A stone rolled down a hill whether or not anyone saw it. Reality was external, objective, and absolute. But as scientists began to explore the invisible quantum realm, that certainty dissolved into something far more mysterious. The observer's role emerged as one of the central enigmas of modern physics. When we look closely at subatomic particles, such as electrons or photons, they behave like waves, diffuse, spread out, existing in many possible states at once. Yet, when they are measured or observed, they seem to decide, on a definite position, as though the act of looking forces nature to make a choice. This strange transformation, known as wave-function collapse, suggests that observation itself determines the outcome. Without an observer, there is only potential. With observation, there is reality. This principle is beautifully demonstrated in the double-slit experiment, where particles act like waves when unobserved but turn into solid particles when measured. The experiment doesn't just test the nature of light or matter. It questions the nature of existence itself. Does reality remain undefined until it is observed? Is the observer somehow woven into the very structure of the universe? Physicists like Niels Bohr and Werner Heisenberg believed that observation was not a passive act, but a key part of physical law. The observer and the observed are inseparable, they argued, bound together in a single system. In contrast, Einstein resisted this view, insisting that the moon continues to exist whether or not we look at it. Yet, the experiments kept pointing toward a participatory universe, one that seems to acknowledge the presence of the observer. The observer's role is not limited to human consciousness. It may extend to any form of measurement or interaction. Still, the philosophical weight remains. The idea that reality is incomplete without observation, that what we perceive helps shape what is. The observer becomes a bridge between possibility and actuality, transforming potential events into tangible outcomes. In this way, physics no longer sees the observer as a spectator, but as a co-creator. The universe is not a silent machine ticking away. It is an ongoing conversation between matter, energy, and awareness. Each observation adds a new note to the cosmic symphony, defining what is real in that fleeting moment. The observer's gaze, once thought insignificant, has become one of the most powerful forces in nature, a reminder that reality, at its deepest level, may be a shared creation between the universe and those who seek to understand it. Among the many mysteries that reshaped modern physics, the double-slit experiment stands as one of the most astonishing windows into the nature of reality. It is not just a test of light or particles, but a profound exploration of how observation itself changes the behavior of matter. The experiment begins with a simple setup. A beam of light or particles like electrons is directed toward a barrier with two narrow openings, and beyond it is a screen that records where each particle lands. When no one observes which slit the particles pass through, they create an interference pattern on the screen, a series of light and dark bands that reveal wave-like behavior. Each particle, in some mysterious way, seems to pass through both slits at once, interfering with itself like a ripple on water. But the moment detectors are placed to see which slit the particle actually passes through, the entire pattern changes. The interference disappears, replaced by two distinct clusters, as if the particles suddenly became tiny solid objects choosing one path or the other. The very act of observing destroys the wave-like behavior and forces the particles to behave as particles. This transformation is not a matter of mechanical disturbance. It is a fundamental shift in the nature of the phenomenon itself. Observation changes what is real. This strange dual behavior of light and matter, behaving as both wave and particle, lies at the heart of quantum mechanics. Before observation, an electron exists in a state of superposition, meaning it has multiple potential positions and momenta simultaneously. Once observed, this superposition collapses into a single, definite state. The experiment does not merely reveal how particles move. It shows that reality at its smallest scales is not fixed until measured. It exists as a cloud of probabilities rather than as concrete fact. The implications are profound. It suggests that reality does not simply unfold on its own, but responds to the act of measurement. Some physicists interpret this to mean that information, not matter, is the fundamental substance of the universe, that the universe exists in a haze of possibilities until an interaction, an observation, or an exchange of information gives it definite form. Others have gone further, proposing that the observer's consciousness might be linked to this collapse, though such ideas remain controversial and philosophical. Still, the double-slit experiment continues to challenge the limits of our understanding. Even when conducted with single electrons or massive molecules, the same mysterious pattern emerges, and the same transformation occurs under observation. It is a timeless reminder that the universe is not as simple as it seems, that the act of watching is not separate from the act of being. In its quiet simplicity, the double-slit experiment captures the essence of quantum mystery, a reality that dances between possibility and certainty, forever shaped by the observer's gaze. In the strange world of quantum mechanics, one of the most intriguing ideas is the collapse of the wave function, the moment when potential becomes reality. Before observation, every particle exists in a state of uncertainty, described by a mathematical wave function that represents all the possible places it could be, all the energies it might have, and all the directions it could move. It is a cloud of possibilities, a shimmering web of what could happen rather than what has happened. But when a measurement is made, something remarkable occurs. The wave function collapses, and from countless possibilities, only one becomes real. The particle takes on a definite position, energy, or momentum. This concept challenges everything that classical physics once stood for. In Newton's universe, objects were always definite. Their properties existed whether or not anyone measured them. But in the quantum world, the act of measuring does not merely reveal a property, it helps to define it. The collapse of the wave function is not just a mathematical step in an equation. It represents the point at which the potential universe narrows into a single experienced reality. What makes this so mysterious is that no one knows exactly how or why this collapse happens. It is not explained by any physical mechanism, yet it is at the heart of every quantum experiment. To visualize this, imagine Schrödinger's famous thought experiment of a cat locked in a box with a radioactive atom that may or may not decay. According to quantum law, until the box is opened and observed, the atom exists in both decayed and undecayed states, and so the cat is both alive and dead at the same time. Only when someone looks inside does the wave function collapse into one outcome, a living cat or a dead one. The act of observation transforms ambiguity into reality. This idea raises deep philosophical questions. Does the collapse require a conscious observer, or does it occur whenever any physical system interacts with another? Some interpretations, like the Copenhagen view, suggest that observation plays an essential role, while others, such as the many worlds interpretation, argue that all possible outcomes occur simultaneously in separate universes, and what we experience is just one branch of that cosmic tree. Whatever the interpretation, the collapse of the wave function shows that the universe is not a static, predetermined entity, but an unfolding of possibilities. Reality, it seems, is participatory, shaped by interaction, by measurement, by the very process of being observed. In every moment, the infinite potential of the quantum world narrows into the single stream we call experience. The collapse is not just a scientific concept. It is a reminder that the world we perceive is not entirely separate from us, that existence itself may depend on the delicate interplay between possibility and perception, between the unseen and the seen. The question of observation in physics does not end with science. It opens a doorway to philosophy, where ideas about existence, reality, and knowledge collide. When quantum theory revealed that measurement could alter the outcome of an experiment, it did more than challenge scientific assumptions. It reshaped our understanding of what it means for something to be. The philosophical implications of observation reach into the deepest layers of human thought, touching on the nature of reality itself. If the act of observing can change what is observed, then can we still claim that there exists a universe independent of us? Or are we part of a cosmic system in which the observer and the observed are inseparable? In classical philosophy, thinkers like Descartes and Kant had already debated the role of perception in shaping experience. Descartes claimed that human thought was proof of existence. I think, therefore I am, while Kant argued that our minds organize reality through categories like space and time. But quantum physics takes these ideas further, suggesting that our perception does not just organize reality. It may actively influence it. When scientists discovered that observation determines the behavior of subatomic particles, they encountered a truth that philosophers had long intuited, that the act of knowing changes the known. This connection between mind and matter blurs the traditional boundaries between science and philosophy. Physicists like Niels Bohr embraced this unity, arguing that we can never speak of reality without including the observer. Einstein, however, resisted this view, insisting that the moon exists whether or not anyone looks at it. Yet, the experiments kept challenging his confidence. Quantum theory seemed to suggest that the universe was not a set of fixed objects, but a web of relationships, events that only gain meaning through observation. For philosophers, this raised timeless questions. Is reality created, discovered, or both? Does the universe possess an independent existence, or is it a participatory process that emerges through interaction and awareness? Some thinkers even saw parallels with ancient philosophies. In Eastern traditions like Buddhism, for example, reality is seen as interdependent and shaped by perception. Quantum theory, in its own way, seems to echo that insight. The philosophical implications of observation remind us that science is not just about equations and experiments, but about meaning. It shows that our search for knowledge is deeply intertwined with our place in the cosmos. Every observation is both an act of discovery and an act of creation. The universe does not reveal itself passively, it responds to inquiry. In this sense, observation is not merely about seeing, but about participating in the unfolding of existence. The more deeply we look into reality, the more we realize that reality looks back, that in every act of observation, the cosmos and consciousness meet, defining each other in the timeless dance of being. Among the most thought-provoking questions raised by modern physics is whether consciousness itself plays a role in shaping reality. The connection between the observer's mind and the quantum world has fascinated scientists and philosophers alike, hinting that the boundary between perception and existence might not be as firm as once believed. When experiments revealed that observation can change the behavior of particles, some began to wonder if the mind, the very act of awareness, could be a participant in the creation of physical reality. Though science remains cautious about linking consciousness directly to quantum mechanics, the idea continues to inspire deep reflection about the relationship between thought and the material world. In quantum theory, observation transforms probabilities into actual outcomes. This process, often called wave function collapse, seems to occur when information about a system becomes known. But what does it mean for something to be known? Does it require a conscious observer, or can a machine or a random interaction serve the same purpose? Some interpretations, like the consciousness causes collapse hypothesis, suggest that awareness is essential, that the universe requires conscious observation to bring potential events into existence. In this view, the mind is not separate from matter, but a participant in the unfolding of the cosmos. Others argue that consciousness need not be involved at all, that collapse occurs simply when any form of interaction happens, whether through a photon hitting an atom or a sensor recording a result. Yet even this mechanical interpretation leaves open a deeper question. What is consciousness, and could it, in some subtle way, be entangled with the very fabric of reality? The boundary between the subjective world of thought and the objective world of matter has never been so uncertain. Philosophers have long suggested that consciousness and reality are intertwined. From ancient Eastern philosophies to modern idealism, many traditions hold that awareness is not a byproduct of the universe, but a fundamental part of it. Quantum theory, unintentionally, revived these old debates in scientific form. The strange truth is that no one fully understands how the mind fits into the physical picture. Neuroscience explains how the brain processes information, but not how subjective experience, the feeling of being aware, arises. Quantum physics, in turn, shows that reality depends on observation, but does not explain what observation truly is. This intersection between consciousness and quantum mechanics remains one of the great frontiers of thought. Whether the universe requires observers to exist, or whether consciousness is simply another outcome of its laws, the mystery unites both science and philosophy in a shared pursuit of understanding. Perhaps, in the end, consciousness and reality are not separate at all, but two aspects of the same vast mystery, the universe knowing itself through the eyes of those who observe it. As the boundaries of quantum theory continue to expand, the discussion of observation leads us beyond physics into a vision of the universe that feels almost spiritual in its depth. The idea that the act of measurement can alter reality forces us to reconsider humanity's place in the cosmos. We are no longer mere spectators of a mechanical universe ticking away on its own. Instead, we appear as participants in a dynamic, responsive reality, a universe that evolves through interaction. This understanding suggests that the world is not a fixed stage where events unfold independently, but a living process, shaped by the interplay of possibility, observation, and existence. Modern experiments and interpretations have shown that particles, fields, and even large systems behave in ways that depend on how and whether they are observed. This has given rise to new philosophical perspectives that view the universe as relational rather than absolute. Reality, in this sense, does not exist as a collection of isolated things, but as a network of connections, where each event depends on its interaction with others. It is as if the universe is a grand symphony, and observation is the note that gives the music its form. The observer and the observed, the question and the answer, are threads woven into the same cosmic fabric. This view has profound implications for how we see ourselves. If observation participates in shaping the universe, then consciousness and curiosity become more than biological traits, they become creative forces. Each act of seeing, thinking, and questioning contributes, however subtly, to the unfolding of the cosmos. The boundary between science and meaning begins to blur, revealing a vision of reality that is both rational and poetic. The observer effect reminds us that knowledge is not neutral. It carries power, responsibility, and wonder. Some scientists describe this emerging understanding as a participatory universe, an idea championed by physicist John Archibald Wheeler. He suggested that the universe does not exist fully formed, but is continually brought into being through the act of observation. In this vision, we are not outside looking in, but inside looking deeper, part of the very process we strive to understand. The universe, through us, becomes aware of itself. This final realization transforms observation from a mere scientific concept into a profound philosophical truth. The act of observing, of measuring, of knowing, is not separate from the act of being. The observer and the universe are inseparable partners in the great dance of existence, shaping one another moment by moment. As quantum science continues to reveal the delicate balance between possibility and reality, it reminds us that every act of awareness connects us to the heart of creation itself, that in every gaze, every thought, every question, the universe is not only being seen but is, in a sense, seeing back. In the quiet halls of science, where curiosity meets the unknown, one of the most profound questions humanity has ever asked continues to echo. What truly happens when we observe something? For centuries, observation was thought to be the most innocent act of all, the simple process of looking at the world, recording what is seen, and uncovering the laws that govern it. Yet, as the understanding of physics deepened, it became clear that the act of observation was far from passive. It was, in fact, one of the most mysterious and transformative elements in the nature of reality itself. From the earliest days of scientific thought, observation stood as the cornerstone of discovery. The great pioneers of classical physics, Galileo Galilei, Isaac Newton, and others, built their understanding of the universe through careful observation and measurement. When Galileo lifted his telescope toward the heavens, he did not change the stars. He merely revealed what was already there. When Newton studied the motion of falling apples or the orbits of planets, he believed he was uncovering timeless truths that existed independent of any observer. Observation in that era was seen as a window, clear, objective, and separate from the world it looked upon. For classical physics, the universe was a grand clockwork, a machine operating with absolute precision. Every particle, every planet, every motion could be predicted if one knew the initial conditions and the laws that governed them. Observation was the tool by which those laws were uncovered, but it had no effect on the machinery itself. The observer was an outsider, detached from the system. It was a comforting world view, one that painted the cosmos as rational, predictable, and ultimately knowable. Yet, as the 19th century gave way to the 20th, cracks began to form in this vision of certainty. Scientists began probing deeper into the invisible world of atoms, electrons, and light, realms far smaller than anything the human eye could see. What they found defied the principles of Newtonian order. The neat lines between the observer and the observed began to blur, and the act of measurement, once considered neutral, began to show strange and unexpected power. At the heart of this transformation lay a new field, quantum physics. Unlike classical mechanics, which dealt with macroscopic objects that behaved predictably, quantum physics revealed a microscopic universe governed by probabilities, uncertainties, and dualities. Light, once thought to be a simple wave, also behaved like a particle. Electrons, the tiny building blocks of matter, could exist in multiple states at once. When not observed, they spread out as waves, existing in a cloud of potential positions. But when measured, when an observer looked, they seemed to make a choice, appearing in one definite place. This was the birth of the observational mystery. The very tools that had once revealed truth now appeared to shape it. The act of looking was no longer a passive process, but an interaction that could alter the outcome of an experiment. In the famous Double-Slit experiment, for instance, particles like electrons or photons were fired at a barrier with two narrow slits. If left unobserved, the particles passed through both slits at once, behaving as waves and forming an interference pattern on a screen behind the barrier. But when scientists tried to determine which slit each particle went through, by placing detectors to observe them, the pattern changed. The interference vanished, and the particles behaved like solid objects passing through one slit or the other. It was as though the universe itself responded differently depending on whether or not it was being watched. The experiment seemed to whisper something profound. That observation was not just a way of gathering information, but a force that determined reality itself. This idea was deeply unsettling. It challenged the long-held belief that the universe existed independently of human perception. The notion that a conscious observer could influence the behavior of matter at its most fundamental level blurred the boundary between mind and matter, between science and philosophy. The observer, once the neutral spectator, now seemed to be part of the play. Physicists such as Niels Bohr, Werner Heisenberg, and Max Born wrestled with this mystery. They realized that at the quantum level, reality did not behave like a collection of solid, well-defined objects. Instead, it existed as a cloud of possibilities described by what is known as a wave function. This wave function represented all the possible states a system could occupy, every potential position, momentum, and energy level. Only when a measurement was made did the wave function collapse, selecting one outcome from the many. In other words, before being observed, a particle existed in a superposition of all possible states. Observation forced it to choose. To illustrate this strange behavior, physicist Erwin Schrödinger proposed his famous thought experiment involving a cat sealed in a box with a radioactive atom, a Geiger counter, and a vial of poison. If the atom decayed, the counter would detect it, triggering the poison and killing the cat. If not, the cat would remain alive. According to quantum theory, until the box was opened and an observation was made, the atom existed in both decayed and undecayed states, meaning the cat was both alive and dead simultaneously. Only when someone looked did reality decide which was true. Such paradoxes revealed the unsettling consequences of the observer's role in physics. The line between objective reality and subjective experience was no longer clear. It was not simply that observation revealed the state of a system, it seemed to create that state. This realization marked a fundamental shift in our understanding of nature, a shift that continues to echo through science, philosophy, and even art. Yet, the problem was not confined to philosophy. It had practical implications. Quantum mechanics, despite its strangeness, produced results that could be tested and verified. It explained the behavior of atoms, the structure of matter, and the principles of modern technology, from semiconductors to lasers. Every experiment confirmed that the theory worked, but none could fully explain why. How could observation, a seemingly passive act, have such a profound impact on the physical world? Part of the answer lies in the nature of measurement itself. To observe something, one must interact with it. In classical terms, this interaction could be negligible, like watching a car pass without affecting its speed. But at the quantum level, where particles are so small and sensitive, even the slightest interaction can disturb their state. To measure an electron's position, for instance, one must illuminate it with a photon, but that photon, carrying energy, will inevitably change the electron's motion. Thus, the act of observing is inseparable from the act of influencing. Werner Heisenberg formalized this principle in what became known as the Heisenberg uncertainty principle. It states that one cannot know both the position and momentum of a particle with absolute precision. The more accurately one is measured, the less certain the other becomes. This is not a flaw of technology or human limitation. It is a fundamental property of nature itself. The observer and the observed are entwined in an unavoidable dance of uncertainty. In this way, observation in physics evolved from a simple act of seeing to a profound interaction that shapes the fabric of reality. The observer became part of the experiment, and measurement became a dialogue rather than a one-way process. The universe, once viewed as a machine ticking away independently, now appeared to respond to our inquiries, as though it were aware of being questioned. As the 20th century progressed, the philosophical implications deepened. Some scientists accepted the Copenhagen interpretation, the idea proposed by Bohr and Heisenberg that reality exists in a superposition until observed, and that observation collapses the wave function. Others sought alternative explanations. Albert Einstein, though instrumental in developing quantum theory, famously resisted its probabilistic nature. God does not play dice with the universe, he declared, insisting that there must be hidden variables, unseen factors that determine outcomes in a deterministic way. But decades of experiments found no evidence for such hidden variables, strengthening the strange conclusion that observation truly does influence reality at the quantum scale. This new understanding of observation extended beyond the laboratory. It began to influence how humanity perceived knowledge, consciousness, and existence. If the very act of observing changes what is observed, then objectivity, the foundation of science, becomes a delicate balance rather than an absolute. The observer's presence can no longer be erased from the picture. Every act of measurement carries within it the shadow of the observer's influence. Yet, In spite of its philosophical weight, this realization did not paralyze science. It enriched it. It pushed physicists to design ever more ingenious experiments to explore the boundaries of observation. They devised quantum erasers, delayed choice experiments, and entanglement studies, each one probing deeper into how measurement shapes outcomes. Again and again, the results confirmed that observation plays a fundamental role, though no one could quite explain how or why. It is as if the universe is participatory, not fully real until engaged with. This does not mean that human consciousness single-handedly creates reality, but rather that reality itself may be fundamentally interactive. At the smallest scales, the world is not a fixed stage upon which events unfold, but a dynamic field of potentialities awaiting interaction. Observation, then, is not merely about looking, it is about relationship, about the meeting point between possibility and actuality. From this perspective, the nature of observation in physics becomes more than a technical question. It becomes a philosophical meditation on the role of humanity within the cosmos. We are not distant spectators, but participants in the unfolding of the universe. Every experiment, every act of measurement, is a dialogue between mind and matter, between the known and the unknown. The observer, in seeking to understand reality, helps bring it into focus. The paradox of observation challenges the very language we use to describe the world. Words like objectivity, measurement, and even reality take on new meanings. What does it mean to say that something exists, if its state depends on whether it is being observed? Is the universe still there when no one is looking? These questions are no longer purely philosophical. They are built into the equations that describe the quantum world. Today, as physicists probe deeper into quantum mechanics and beyond, the nature of observation remains one of the central mysteries of science. Some theories suggest that reality may be fundamentally informational, that the universe itself operates like a vast computational system, and observation is the process of reading its code. Others propose that observation is not tied to consciousness, but to interaction, that any exchange of energy or information constitutes a form of measurement. Whatever the final answer may be, one thing is certain: observation is not what it once seemed. It is no longer the act of a detached spectator gazing upon an indifferent universe. It is a process woven into the very structure of existence, a reminder that in the quest to understand the cosmos, we are not standing outside of it, but are inextricably part of its unfolding story. As the curtain of the 20th century lifted further, and new generations of physicists took up the torch of discovery, the question of observation deepened rather than faded. What began as a curiosity within quantum experiments grew into a profound dialogue about the structure of the universe itself. The idea that reality depends upon observation seemed almost mystical, yet experiment after experiment refused to dismiss it. The very act of measurement, something so fundamental to science, had become the heart of one of its greatest puzzles. To grasp the modern understanding of observation in physics, one must look beyond the surface of quantum mechanics to the strange ways in which particles behave when they are entangled. Quantum entanglement occurs when two or more particles become connected in such a way that the state of one instantly influences the state of the other, no matter how far apart they are. This bizarre link defies the classical notion of space and time. When one entangled particle is measured, the other immediately knows, collapsing into a corresponding state. Einstein called this phenomenon spooky action at a distance, for it seemed to violate the rule that nothing could travel faster than light. Experiments later confirmed that entanglement is real, and it depends again on observation. When no measurement is made, both particles exist in a superposition of possibilities. But the moment one is observed, the other instantly adopts a complementary value. Observation, it seems, not only defines local reality, but can instantaneously shape distant reality as well. The universe appears to operate as an indivisible whole, and observation may be the thread that connects its parts. In this light, observation takes on an even deeper meaning. It is not just a matter of human eyes watching or instruments detecting. It is the fundamental process through which the universe determines its own state. Some physicists describe the universe as a great web of relationships, where observation is the process of updating connections. Every particle is entangled, every interaction a form of measurement, and every measurement a choice that defines what is real at that moment. This participatory picture of reality began to reshape scientific and philosophical thought in unexpected ways. John Archibald Wheeler, one of the leading physicists of the 20th century, proposed that the universe is not merely observed but participatory, that the presence of observers is necessary for the universe to come into being in its present form. He suggested a radical idea known as the participatory anthropic principle. According to this view, the universe gives rise to observers who, through their observations, bring the universe itself into a concrete state. In other words, we are not just products of the cosmos. We are co-creators in its ongoing evolution. Wheeler illustrated his idea through the delayed choice experiment, a modern twist on the classic double-slit setup. In this experiment, the decision to observe or not observe a particle's path can be made after it has already passed through the slits, and yet the results still change based on that delayed decision. It is as though the particle knows in advance whether it will be observed and adjusts its past behavior accordingly. The implication is staggering. Observation does not merely reveal the present, it appears to shape the past as well.